All right, welcome to Unit 4, Day 12. This is Part 2. This section is required for honors chemistry, but is optional for fundamentals of chemistry. So in this video, we're going to address the second part of this section of your project, choosing one of the 5 properties you listed for your substance to explain how this property makes the substance useful. So the main thing is what is this So main thing you need to think about is what is the substance used for and sort of link it to that property. What we're going to go over here are things that you can think about when it comes to those specific properties. There's like 3 that we'll go over that may be helpful. You can also choose to do your own thing as well, but this may be helpful in terms of getting you to start thinking, because a lot of times properties can have multiple uses, and so it helps you to sort of narrow it down. All right, so the first property we'll look at is phase, and for phase we're talking specifically of something's a solid, liquid, or gas. And one thing that's important about phase is the phase is important in terms of how easy it is for something to transport, or it also can be important in the delivery of that chemical. When I say delivery of that chemical, if it's something that is involved in the body, how it's delivered to cells, for example, or if not, how it's delivered to the substance or the thing that it's used in. So let's look at an example. Let's say acetaminophen, which is the active ingredient in Tylenol. That is a solid. So I want you to pause for a moment. We know that acetaminophen is a solid and acetaminophen is a medicine. How would that be useful? Okay, so this, you may have come up with something different, but for me, what I thought about, if it's a solid, and then that makes it easier for people to carry it around. And that's useful because you're not necessarily always in pain, but on occasion you may need to take some. So if it's a liquid, you have to worry about it spilling in your bag, but if it's a solid, then it makes it easier to transport. So you can say something like, because acetaminophen is a solid, it can be easily transported. That should say people, by people, not peoples, who can then take it to relieve pain when necessary. Okay, so that will be something that you could say for that section. Just a simple sentence. Another example or property we can talk about is solubility. So solubility, remember, according to the likes dissolve likes rules, polar substances will dissolve polar substances, and likewise nonpolar substances will dissolve nonpolar substances. So something that's polar will dissolve in water, and something that's nonpolar will dissolve in an oil, for example. Now, that's important for how a chemical is absorbed by the body. So, for example, vitamin B6 is polar, so it's soluble in water. And that makes it easier for the body to absorb it, right? So most of our body and our cells are made of water, so it makes it easy for the body to absorb it. It also, on the flip side, makes it easier for the body to expel it. So a lot of times when you take these vitamins, these water-soluble vitamins, you will excrete some of it out through sweat or through urine. So what if you had a fat-soluble vitamin like vitamin D? So vitamin D is nonpolar, so it's not going to dissolve in water, but it will dissolve in fats. And that's important because it can be stored in fat cells. And fat-soluble vitamins that are stored in fat cells, you can store them in your body a lot longer. Okay, so let's look at another example when it relates to solubility. Let's look at the example of urea. So we saw in part 1 that urea is used in fertilizers. And if you look at the structure of urea, you'll find that it is polar. So that means it's soluble in water. Why do you think that will be helpful if urea is soluble in water? Okay, so maybe you thought of something different from me, but what I thought of was, well, if it's soluble in water, then it will get dissolved in water, and that can happen when it rains or when you water the ground, and so that helps to make it get absorbed into the soil, and also helps distribute it as well. Okay, so we could say something like, in this case, because urea is soluble in water, it can be easily absorbed into the soil and into the roots of the plants whenever it rains or after the plant is watered. So again, we're linking the idea of it being soluble or being able to dissolve in water to its use, which is fertilizer. Another example, this was the last one for solubility, involves sodium lauryl sulfate, which again is used in soaps. And one thing that's important about sodium lauryl sulfate, it has an ionic end. So you see the metal here, sodium, and the nonmetal. And you notice that you have your cation and your anion. So that's my ionic end, which will dissolve in water. This other end here, which has this long, these are, remember, wherever you see these lines with no atoms written, those are carbons with hydrogens attached. So this is a long hydrocarbon chain. That part is nonpolar. Remember, carbon hydrogens, substances, which are also known as hydrocarbons, are nonpolar. So that's going to dissolve the oil and the grime. All right. And so something like sodium lauryl sulfate is amphiphilic. It has a polar part and non-polar part, and that's why it's useful in soaps, because it helps wash away the grime in the water. So I just want to sort of illustrate that for you. So here you have, here's your skin that's on the surface, and here you have a clump of dirt. Now, dirt oftentimes will sort of aggregate where there's oils on your skin. So water won't wash that off because the oil is nonpolar and the water is polar. So what happens is with the soap molecules, it has a polar part and a nonpolar part, right? That nonpolar part, where you have that long hydrocarbon chain, is going to surround the dirt. And then the polar part, which is sticking out on the outside, can get dissolved in the water. So it sort of helps to wash that away. Once all of the dirt particles are surrounded by the soap molecules, it can get washed away into the water. So now you may be thinking to yourself, well, that's cool and all, but how can I tell if something is polar? Remember that checklist that we learned about all the terminal atoms having to be the same and no lone pairs in the central atom for it to be nonpolar? Well, that doesn't work for larger molecules because they don't have a central atom. So what do we need to look for? In that case, what you're going to look for are these groups that I'm going to list in a moment. And the more of these groups that you see in a molecule, the more polar it is. So what are the groups? One thing to look for are charges, if you see groups that have plus or minus signs. Another group or thing to look out for are where you see OHs. These are called hydroxides. Okay, so here, for example, you see some OHs. These are things to look out for. Where you see a carbon-oxygen double bond and or a Cu group. Remember, Cu groups are the carboxylic acids. The more of those you see, the more polar it's going to be. We also have amines, which are nitrogen containing compounds, or anything with just typically with the nitrogen in it. So here you see, for example, you have a nitrogen. Well, the more of those that I have, the more polar it's going to be. And also halides, chlorine, fluorine, bromine, for example. The more of those that I see, the more polar it's going to be. So an example of vitamin B6, which is polar, notice how many of those groups that we have, right? That's what makes vitamin B6 polar, because we have a lot of those groups. Now you may be thinking, well, what does it have to do with it dissolving in water? What do those groups have to do with dissolving in water? That has to do with something called hydrogen bonding, which is a force that holds molecules together. It's a pretty strong force. Now, we're not learning about these, what are called intermolecular forces, the forces between molecules, but I will link it in an extension activity in case you're interested in learning more. Okay, so we already looked at how to tell if something is polar by looking for groups like hydroxides, OHs, and amines, nitrogens, etc. But what about for nonpolar? What should we look for in that case? And for nonpolar molecules, you want to look for hydrocarbons, things with just carbon and hydrogen in it only. And so those would be like long chains or rings. So for example, we have a long chain here like octane. Once again, remember when you see these lines, these are carbons with hydrogens attached, right? There are no atoms written there. And then there's rings that you may see that look like that. So the more of those that you have in the molecule, the more nonpolar it is. All right, the last thing we're going to talk about are acids. So we've learned to recognize an acid from their chemical formula with an H in the front and a Cu group in the back. But that's not always possible when someone writes a condensed form of the chemical formula. For example, for vinegar, you can write it as CH3COOH. Or what you can do is you can put all the carbon, hydrogens, and oxygens together, and then it will be C2H4O2. So that doesn't show you a Ku group. So in that case, then how do you recognize it? You can look for a Ku group in the structural formula. So when you have the image of the molecule, you look to see if you can find that group. Or you can, or we'll say an acid in the name, like salicylic acid. So when I say a Ku group, remember this is what we're talking about. This is what they look like: carbon with an oxygen double bond and an OH group. And so if you have a molecule like this and you're looking at the molecule, whoop, there goes a Ku group and there goes a Ku group. So you know that this is an acid. Now, why is that important? Acids are reactive and they do things like neutralize bases and vice versa. So bases will neutralize acids as well. The Ku group is polar, so many acids will dissolve in water. They react with metals, and a lot of our cells, the cells in our body, will process or metabolize acids. So something we may take in that's not in acid form, by the time it gets to our cells, it's in an acid form because that's the way our cells like it. All right, so when it comes to acids, you want to just sort of think about their reactivity. So in summary, here are some things that you can think about to answer this last part. You can think about the phases, the solubility, and whether or not it's an acid. That will give you information about reactivity or solubility as well. You're welcome to use some of the things that I showed here. You're welcome to use this information as much as you would like. It has to be in your own words, of course, or you can completely come up with your own, but it gives you a sense of what I'm expecting. All right, that's it for this video. Good luck with your work. Have a quality day.